Good morning, everyone. My name is Jeka
I'm
Shashni.
Sabrina Alia.
I'm Anas Shafiq bin Mat Saad.
I'm Muhammad Idham Lamla, and we from K3 will present our final year design project about the production of glycerol carbonate.
Good morning, everyone. The table below shows the list of improvements that are made based on the chapter.
Glycerol carbonate is produced from urea and glycerol. To produce glycerol carbonate in liquid form, we need to have an optimal parameter for the production to succeed. The production is at 140 Kelvin and 101 kPa at backpack reactor, and catalyst uses time release 15. GC is act as emollient since it has bacteriostatic properties that can kill bacteria and have low toxicity, and of course it has the moisturizing ability.
The economic analysis from the stoichiometry equation, we derive for the rate determining equation and generate a graph of concentration against time, and our limiting reactant is urea. From the prices for each component, we plot for economic potential curve for level 2, level 3, and level 4. And the curve started to become constant at the conversion value of 0.4, which is close to the literature study.
Good morning, my name is Jeka Shashni, and now I will explain on the aspect of economy analysis. There are a few components that is being projected in economy analysis. First is a return of investment, also known as ROI, which is equivalent to 0.28 per year. Since the value of ROI is higher than the MAR, which is equivalent to 0.16, the project is said to be profitable. The payback period is equivalent to 3.67 years. The PVP is approximately equal to the PVP reference, which is 3.96 year. The net return is equivalent to 114.67 million per year. Since the value of the net return is positive, the project is known to be profitable. The net present value, also known as NPV, is equivalent to 154.47 million per year. Since the NPV is positive, the project is said to be profitable and also considerable. The net discounted cash flow rate of return, DCFRR, is equivalent to 0.24. Since the value of DCFRR is higher than the MAR, which is equivalent to 0.16, the plant is said to be profitable and also considerable.
For plant location, based on the score rating that we have done out of 3 proposed locations, here KIIT Kapar 2 Jalan Kapar obtained the highest score due to its location that fulfill the primary factor which may greatly affect the sustainability of the plant and its productivity. Thus, it has been chosen as our plant location. For our plant location, the land area availability would be around 8 acres, which costing about 17 million ringgit Malaysia, according to the property guru posted by Mr. Hatatio. The location chosen basically preferred for medium and heavy industry. The raw material required for urea will be supplied from the edible oil industry, and the crude glycerol will be supplied from Petcoke Energy Biodiesel plant. Other than that, our plant location is 0.2 km from the main road Jalan Kapar with the road access, water, and the electricity that are applicable from Pengurusan Air Selangor and Tenaga Nasional Berhad. Since the plant location is located about 2 km from the residential area, the availability of the manpower is expected to be sufficient for the operation needed to operate the plant.
The process starts with the naturation of crude glycerol using phosphoric acid in the CSTR reactor. The solution is transferred into microfiltration to separate sodium phosphate and ash. Then, the mixture is transferred into centrifugation to remove fatty acid. After that, the mixture enter dividing wall distillation column to separate into 3 main components, which are methanol, water, and purified glycerol. The purified glycerol then transferred into backpack reactor, and the urea is added into backpack reactor. Inside the backpack reactor, there are embellished 15 that use as catalyst for the reaction. The product from backpack reactor is sent into flash drum to remove ammonia gas. Then the mixture is sent into clarification tank to remove unreacted urea to be recycled into PBR bag. Next, the distillation column used to separate unreacted glycerol and recycle it into PBR.
Pinch analysis method is used to determine the pinch point. Pinch point for hot stream is 90 degrees C and 110 degrees C for the cold streams. Heat recovered through this process is about 47%. The red streams indicate the transfer of heat, while the blue streams indicate the heat is being absorbed.
Below shows the PNID before HAZOP. As you can see, we have included the control system for each of the equipments. Diagram below shows the PNID after HAZOP. We have included the alarm system and bypass valve to increase the safety of our production plant.
This is the detailed design of CSTR R101. CSTR R101 is designed to use ellipsoidal head for both top and bottom, while for the shell vessel is designed to use cylindrical shape. The parameter applied for the corrosion allowance is 2 mm and the joint efficiency is above 0.85. And the ratio of the height to diameter is about 2 to 1 with the maximum allowable stress of 20,000. The working volume of the CSTR after being applied 10% safety factor to prevent overflow is 49.07 meter cubic, and the type of the impeller used is anchor impeller with the thickness of this of 123 mm. CSTR is designed to operate at 1 bar and 60 degrees Celsius, and the material used for construction is stainless steel type 316. And the detailed design and specification of the CSTR R101 is shown in this table. This is the mechanical drawing of CSTR R101 that have been drawn based on the calculation from design specification. And the corrosion allowance used is 2 mm and the inside diameter is 3149 mm, while for the height of the reactor is 6298 mm, and the material used for construction is stainless steel type 316, and the skirt design is conical skirt with the skirt support of the double ring with cassette, and the flank design is well net flange, and the bolt size is M24, and the impeller used is anchor impeller.
The next unit is cooler. This cooler is responsible for cool down crude glycerol and fatty acid that coming from reactor from 50 degrees C to 25 degrees C. Cold water is used as coolant to cool down all the components. This slide shows all the parameters involved in designing the cooler. The construction material chosen for this cooler is carbon steel, and the total length for this cooler is 1.78 meters. Process fluid enter the tube through flanges at the top and exit through the bottom flanges, while service fluid enter the shell through the top flanges at the backside of cooler and exit at the bottom. The baffle design are separated by 2 passes, which allow 40 tubes to be placed at each passes. Lastly, the design saddles are determined by using an SME by looking at the maximum weight load that can the saddle holds. This slide will show the detailed design of flash drum. The flash drum is used to separate ammonia gas. This operation results in the total removal of ammonia in the vapor phase. In stream 33, that contains a mixture of vapor liquid coming out from the condenser, will enter the flash drum, and vapor will be removed from overhead from the flash drum in stream 34, while the remaining liquid will collect at the bottom of the drum and be removed in stream 36, which is composed by unreacted glycerol and urea and the product, which is glycerol carbonate. The flash drum is operated at 50 degrees Celsius and 101.33 kilopascal. The corrosion allowance state for this flash drum is 2 mm. This table shows the detailed design of the flash drum. This slide shows the mechanical drawing of the flash drum. The flash drum is drawn based on the detailed design and the mechanical design calculated. The material type for this vessel is stainless steel type 316, since it involves ammonia, which is a quite corrosive material. In the flash drum, there is a demister pad, which is an equipment used to remove induced liquid droplets from a flow of gas. The demister pad is sometimes mounted below the vapor liquid separator's top vapor outlet. This demister pad helps empty drums by increasing the efficiency of gas-liquid separation. Empty drums requires large sizes and rely on a long residence period to separate liquid from vapor. The degree of separation can be accomplished by using smaller vessels by using this demister pad. This is the cross-sectional view of flash drum with demister pad. The support chosen for this vessel is single plate with cassette, and this is the cross-sectional view of a welding neck line.
My name is Jega Shashini with metric number of A163352. Will explain on the design of the distillation column D102. The function of this column is to separate glycerol carbonate from glycerol. The design temperature is 216 degrees Celsius. Meanwhile, the design pressure is 324.611 kPa. The distillation column is designed under using internal pressure. The assumption used while designing this distillation column are steady state and no chemical reaction are involved. The table below shows the detailed design of the distillation column D102. The diameter of the column is 1.845 meter. The height of the column is 9.23 meter. The actual stages are 14 stages, and the 5th stage is located at the 8th stage. Next, I will explain on the mechanical design summary of a distillation column D102. The material selected is carbon steel SA537, since the mechanical properties of the carbon steel, which is greater resistant to atmospheric corrosion, and it is also more economical. The corrosion allowance is 2 mm since severe corrosion is not expected. The top and bottom of this distillation column is torus-spherical and the body is cylindrical. The stress calculation conducted shows that the stress analysis and elastic stability shows that the design are safe to be used. The type of vessel support is straight conical flask. This gives more stability and also mechanical support to the structure. Mechanical design of the distillation column is shown in the slide. The distillation column is designed based on the calculation made during the detailed design and also mechanical design. This is the top view of D102. Meanwhile, this is the cylindrical part of the distillation column. This is the design for the sieve plate, the design for straight skirt support, the design for bedding neck flange, and also the design for blind flange.
For this slide, I will explain about the mechanical design for pair-back reactor R102. This reactor is conducted in the atmospheric pressure and at 140 degrees Celsius. The material used to build this reactor is stainless steel type 316 as is the most recommended for acid and chloride corrosion resistant. Other than that, it also offers strict hygiene and cleanliness standard which is suitable for our product. And then for the measurement of this reactor are shown in the table provided. We continue to mechanical design for pair-back reactor R102. The design and measurement is not to scale. The design is drawn based on calculation in detail and mechanical design. As shown, bottom unit is the side view cross-section of the reactor, while both of top unit is the side view of the bed in the reactor. Meanwhile, the left unit is cross-section of skirt support and the right is cross-section of welding neck flanks. For this slide, I will explain about the safety plan layout for our factory. Firstly, the north direction for this layout is to the top and the wind direction is to the left of this drawing. Our factory can be accessed from two gates. The first gate is at the left of this drawing and another one is located at the right position of this drawing. The first gate is purposed as a main gate, meanwhile the second gate is for supplier and heavy vehicle use. Next, the administration building, training center, medical center and cafeteria are located near to the main gate. This is to make sure most of the worker is far away from hazard area. Then, we move to hazard area, which is the area that chemical operation had been conducted. That area is placed on the top section. And to minimize any accident, emergency response team and firefighter station are located in the middle of factory. This will make sure the team can respond immediately when an accident occurs. After that, to minimize the waste treatment plant is placed at bottom left, which is easier to heavy vehicle to send the waste into the quality alarm. Thank you.
This is the PFD of our wastewater treatment plant. As you can see, the waste that consists of water and methanol from stream 24 in the main process will enter the aeration tank. The aeration tank is designed to facilitate the biological treatment for COD and BOD reduction, where this oxygen is being supplied throughout the process. To efficiently reduce the COD and BOD for our effluents, three aeration tank will be used. With this, two of them will be similar in size, while another one will be slightly smaller since the hydraulic retention tank is smaller. However, this three tank contains the same microbes to treat the effluents. Then the waste will enter the clarifier to separate the liquid waste and solid waste based on the gravity force. Then the sludge will enter the sludge thickener tank, which is normally the first process of removing moisture in sludge. Since our sludge contains methanol, we will be using a static thickener free of chemical to avoid any reaction with the already hazardous sludge. Then it will enter the sludge dewatering tank, which is also important to reduce the moisture content of sludge. The solid waste we will store in the holding tank before it's sent to quality alarm for further treatment, while the liquid waste, which is the treated water, will be discharged directly to the river as it follows the standard B for COD and BOD value. For the conclusion, in safety aspect, the most hazardous chemical in this plant is ammonia. In economic analysis, the break-even at production capacity at 125 kilotons per year. The location selected is KIIP Kapar 2 Jalan Kapar is selected for our plant location. The waste management is using aeration method to oxidize the methanol. And for our unit design, every unit will design according to their process with safety consideration to ensure the plant is safe to operate.